Hello. In this video we're going to talk about the basics of hypothesis testing. The first thing that we need to do is talk about some definitions. So a hypothesis is a claim or a statement about a property of a population. A hypothesis test or test of significance. I will never use this term test of significance. I'll always refer to it as a hypothesis test. Is a procedure for testing a claim about a property of a population. The null hypothesis, denoted H sub 0, is a statement that the value of a population parameter is equal to some claimed value. The term null is used to indicate no change, or no effect, or no difference. We test the null hypothesis directly in the sense that we assume or pretend it is true and reach a conclusion to either reject it or fail to reject it. This statement will always contain the symbol equal. This is the value that was previously thought to be true. The alternative hypothesis you can denote in one of three ways: H sub 1, H sub lowercase a, or H sub capital A. I always use H sub capital A. This is a statement that the parameter has a value that is somehow different from the null hypothesis. It always uses either a less than, greater than, or not equal to symbol. This is the value someone believes to be true or they are trying to show as true. In this table we have the different sampling distributions and test statistics that we might use. So if we want to do a test about a proportion, so a good example of a proportion would be the Mendel peas. If a problem were to say that there were 300 green peas and 100 yellow peas, that would be an indication that you would be using a test about a proportion. Or it could say that 73% of the peas that we collected were green. Or it might say that 300 out of 400 peas were green. All of those would be different ways to talk about a proportion. Your test statistic is the standard normal distribution, and the test statistic to calculate it is p hat minus p. P hat, remember, is from your experiment, and this p is the one that we are assuming is true from previous knowledge. And this one, remember, is from an experiment that you're performing. So p hat minus p divided by the square root of pq over n. We could test about a mean of a population. The sampling distribution would be t. You would use this if sigma is not known and you are from a normal population, or if sigma is not known and you have n greater than 30. If n is greater than 30, then it doesn't matter what population you're from, but if you have n that's less than 30, then it has to be coming from a normal distribution. So the statistic here is x bar minus mu divided by s over the square root of n. So again, x bar is from your experiment. Also the s in the denominator is coming from your experiment as well. The second one is also from a mean. You can use the normal distribution, but this is very rare. You can only use it if sigma from the population is known and you're normally distributed, or if sigma is known and your n is greater than 30. So the only difference between having to use t and this z is here you don't know the population's standard deviation, and here you do. And again, this second case is very, very rare. You almost never hear that. If a problem just states that here's what your standard deviation is, then you would be using t. It would have to specifically state, have the word population standard deviation in there, or it would have to use the Greek symbol sigma in order for you to be able to use z. Almost always, though, you're going to be using the t distribution. So this formula is basically the same as the formula for t, it's just that you have sigma instead of s. So that's the only difference in the formulas there. If you want to do a test about a standard deviation or a variance, then we would use the chi-squared distribution. This has a strict requirement that it needs to be from a normal distribution, and our formula is n minus 1 times s squared. So this is your experiment standard deviation squared over sigma squared. So that would be the population or what you're testing. So those are the 4 different test statistics that we have, and basically we'll only be using the 3 here. Oops, sorry, not that one, the T. So those 3 are the 3 that we'll generally be using. So here there are 3 different situations that can happen. So now we're going to talk about how do we set up the null and the alternative hypothesis. Let's take the P example. We grew some peas and we collected them, and we had 280 green peas and 120 yellow peas. We are claiming that 75% green. So when you're writing out your null and your alternative, you always state what your claim is. So the claim is that 75% of the peas are green. So that would be P is equal to 0.75, 75%. And then you write down the opposite of your claim. The opposite of P being equal to 0.75 mathematically would be that P is not equal to 0.75. So whenever you're writing out your claim, the one that contains the equal sign becomes your null. So in this case, H sub 0 would be P equals 0.75, and the alternative is that P is not equal to 0.75. So whenever you have not equal to in your alternative, it's a two-tailed test. So here is sort of a picture of a two-tailed test. So in this red area, if your test statistic that you calculate falls in this red area, we would reject the null. If it falls in the green area, we would fail to reject the null. So these are critical values. And the critical values are based off of the significance of your test. And then, so once you find these 2 critical values, then you can determine where your test, so calculate your test statistic and determine whether you're in the green area or the red area. You'll reject if you're in the red area, and you'll fail to reject if you're in the green area. This alpha is the level or the significance of your test, and when you have a two-tailed test, this alpha gets divided evenly between the 2 tails. It's very similar to when we did the confidence intervals. You may also have a left-tailed test. So in the P example that we were doing before, we could make the claim that p is less than 0.75. With a less than, then that would be a left-tailed, and so all of alpha is in this tail, instead of being split between two tails like a two-tailed test. If you end up in the tail, your test statistic ends up in the tail, then you will reject the null. If you're in the green area, then you would fail to reject the null. You could also have a right-tailed test if our claim was that p was greater than 0.75. Then we would have a right-tailed test. And again, all of alpha is in this area over here. And this works the same way. So this value right here is your critical value. If your test statistic falls in the red zone, you reject the null. If it's in the green zone, you fail to reject the null. The p-value, or probability value, this is the probability of getting a value of the test statistic that is at least as extreme as the one representing the sample data, assuming that the null hypothesis is true. So here's a table of words, but I'm going to go back up to our pictures so that I can talk about the p-value. So in this picture that we have right here, so this red area has an area of alpha. Oops. And this is your critical value. So the critical value and alpha are connected, and then you'll also calculate a test statistic, for example, a t. So you get this t value that you calculated, and you'll plot it along this edge. So let's just pretend that we calculated it and it was right here. So the p-value is the area from your sample statistic out to the edge. So if you have a right-tailed test, it would be the area from this test statistic out to the edge. So if your p-value is bigger than your alpha, then that will tell you that you're in the green area. If you calculated a p-value and it's smaller than alpha, that would mean that the area is less than or smaller than this red area, and that would tell you that your test statistic was inside of the red zone, and so you would reject your null. So big p-value, good, you fail to reject. Little p-value, bad, you reject the null. So the critical region in the left tail, then the p-value would be the area to the left of the test statistic. If the critical region is in the right tail, then the p-value is the area to the right of the test statistic. If the critical region is in two tails, then the p-value is twice the area in the tail beyond the test statistic. The last thing that you'll need to do when you're doing a hypothesis test is to restate the decision using some simple non-technical terms. And so this is the way that you want to make your statement once you're finished. So the first thing that you want to do is figure out where your claim is, and when I write out my null hypothesis and my alternative hypothesis, I write the word claim after whichever one it's in so that I know when I go to make my statement where the claim is. So if the original claim contains the equal sign, so that means that it's in your null hypothesis, then the way that you're going to make your statement is, if you're going to reject the null, you say there is sufficient evidence to warrant rejection of the claim, and then you just restate whatever the claim was. If you're going to fail to reject it, then you say there is not sufficient evidence to warrant rejection of the claim, and then you restate the claim. If the claim is in your alternative hypothesis, then you're going to make the following statements. If you reject, you're going to say the sample data support the claim that, and then restate your claim. And if you fail to reject the null, then you're going to say there is not sufficient sample evidence to support the claim that, and then restate your claim. So I do believe that this table is included in the formulas. Being able to make this statement shouldn't be too bad, because you should be able to just look it up. So these two are if the claim is in the null hypothesis, and these two are if the claim is in the alternative. Okay, so that's it for this video. Let me know if you have any questions, and I hope you're having a great day. Thanks.